Thank you, everyone. Welcome. Hello. So I am going to start. I didn't have an introduction, but I'm going to talk about engineering safe and socially aware systems, but really focusing on collaboration. So the main topic of this talk is that people in AI agents can achieve more. What is the more? I'm going to explain a little bit more later, but through collaboration. So the main focus is how to enable then collaboration between AI agents and between AI and humans. And here I'm using agents in the broad sense, not in necessarily in LLM agents. Okay, but the first question then is, what is collaboration? So I'm gonna present what is collaboration according to two axes. Some of you have already seen the matrix, but around two axes. First is whether we're talking about a single system or multiple systems, and the x-axis is around the cognitive level. So the simplest cognitive level is reflexive. So the output depends on an input. And the second one is the output depend on an input, but also on a state. And that will give us adaptive systems if we're talking about individual system, and connected if there are an ensemble of systems. And then the third level is reason. So any output will depend on, the input, the state, but also the goal we're trying to achieve. And that will give us autonomous systems when we are talking about an individual system, or collaborative systems when we are talking about ensembles. So what collaboration means here in this talk is that reasoning about ensembles of systems to achieve goals. And those ensembles can take multiple forms. They can be purely cyber systems, they can be robots, they can be physical resources, they can be a human and a software system, or they can be multiple groups of humans and systems. And this is the one that we are going to talk to. But regardless of the ensembles, we're always interested in how to achieve goals, how to represent and reason about those goals. So in this talk, I'm going to present three frameworks around that collaboration between humans and autonomous systems. So the first one I will present, and it's called IDEA, Identity-Aware Autonomous Systems, and is how to reason about human, as in group behavior, to achieve goals. The second framework I'm going to present is building on that identity-aware autonomous systems, but actually also providing formal guarantees. So we call it formidable, the formally verified idea. And the third one, and that's kind of a little bit different, is how to represent requirements for those machines, and actually those machines that are already failed. So that's the little extra I'm going to add, and that's represent a framework we call REAL, so requirements engineering for machines that learn. Okay, so the first one, idea. I'm going to start by presenting an example. So a lot of you know already that, robot, AI, and autonomous systems are increasingly used in emergencies. And it's often the case that they are used by first responders. So what we call first responders are, the emergency services, the fire services, the police. And they are often used to provide situational awareness to access extreme environments. And they actually help in first responders, because first responders are usually a scarce resource. So they are sometimes unavailable. So, for example, in the London bombing in 2005, the emergency services didn't even reach until after 20 minutes, and the people there were left alone in the underground. In the Manchester Arena attack as well, the emergency services arrived but weren't able to access because of safety reason. So what happened meanwhile? So the people who we call zero responders, so people who are on the scene, are able to, well, they usually respond to that emergency. And often there is an increasing evidence that when people find themselves in those emergencies, they help each other. There is that notion of cooperation, that social support, and it shows in things like, attacks, but it also shows in like, floods and earthquakes. So also, natural disasters. And that cooperation also help not only during the response, but also afterwards to build resilience and to help people recover, especially when it's a natural disaster event. So why do people collaborate? So one of the things and one of the theories around that is that during emergency, there is that sense of common fate, and that leads to what we call shared identity among survivors. So we're in it together, therefore we help each other. So, for example, with the London bombing in 2005, is you're in the underground, you're just a bunch of individuals, you don't look at each other, and suddenly there is that emergency and you come together, you help those unknown people as well. So that said, not everyone would be part of their shared identity. There will still be people who are pro-self, who will prioritize their own safety. So what also the social identity theory tells us is that by deviating from the group behavior, then there is there's a loss for deviating from the group behavior, and that can be perceived as anxiety or disappointing the group or like lack of cohesion among the group. So why are we kind of can we use that social identity when we design and engineer autonomous systems to deal with that? So the question is then how to engineer autonomous systems, AI systems, to reason about and leverage identity to collaborate with humans. So, and that kind of go a little bit beyond what exists. So, for example, a lot of the drones, the robots that are used by first responders, they have what we call human in the loop. So the first responder is supervising the autonomous agent, or you have the robot reasoning about the first responders, who follows a certain, is an operator, so certain protocol, certain action, well understood, or kind of interacting with one another. But what we want is really kind of not only with the first responder, but the zero responders who may have different behaviors, who you cannot necessarily train to follow certain protocols, but also who have that kind of social grounding, who have that shared identity. So that's what we mean really by human-machine collaboration in those settings. So the bad news, though, is that all that social identity is a psychological state. So we cannot observe it directly. We cannot just deploy sensors and see that social identity and monitor it. But fortunately, there are what we call like identity markers. So there are a lot of identity markers, like people who belong to the same group will have a tendency to be together, to gather together, to move to the same directions. And most importantly, there is a lot of indicators of identity in language. And that's the one we are using. So what we did is we trained and we gathered actually with social psychologists. We gathered a lot of information from past incidents. So we gathered 200 occurrences from a lot of self-report post incident. And then we had like 2 researchers label them accordingly. So symbols of that shared pro-social identity include like references to the we and us togetherness. So something like it would be best for us to not go, or something like that. It indicates social interaction. So even if you don't use the we and the us, there is a sense of a bond. So what do I do now? When you ask someone like that, is already in the sense of coordination. There's also something around shared emotion or emotional support. So utterances such as you have to think about your family, or you have to do it. So that kind of display that sense of empowerment and shared emotion. And something like more around pro-self identities. I'm getting out of here. So we collected those data, and they are publicly available. And then what we did is we trained them. We used BERT. So we had a text classifier that during the evaluation will take some occurrences and then define whether it is more is an indication of that shared pro-social identity, or more of a pro-self identity. And then we have our goals in mind. So we have a sense of, when we are doing the evacuation, we want, for example, to maximize the number of evacuation, minimize the evacuation time, and actually maximize the identity payoff. And based on actually that the theory around which their social identity. So based on that, having the goals in mind and having those multiple groups, we can create a Bayesian game model with basically 2 different players, 2 different agents. So we have the 0 responders and the robot, and basically whether we have a probability of whether the person will develop the shared identity or not. And that probability is only known at runtime, when the system is running and when the person is interacting with the autonomous agents. And based on that, the agent can take multiple actions. They can ask the survivor to help. They can ask a first responder to help. And then, like, this is a bit simplified version of the overall game. But then, based on that, the survivor can still have the agency and can take an action to help or not. So, and based on that, we calculate what is the payoff for the robot, what is the payoff for the person. And by solving that game, we arrive to the best strategy for the robot to take in that specific context with the specified probability. So what we did is we did a lot of simulation. So using an agent-based model that of a transport evacuation hub that was developed, empirically evaluated. And then what we did is we added a robot that goes ahead, and then each person will have those identity markers, and we simulate the speed at which the response happened under different conditions. So, and we have also that available online. You can do it. You can kind of change the strategies, for example, and then you can collect also all the data and use it afterwards. So in a way, the way we did the evaluation is we deployed 3 strategies. We developed a pro-social oriented system, which basically always assumes that people will help. We had the pro-self version agent who actually assumes that people will never help. They will always prioritize themselves. And a robot that will take, that will reason about identity. So the strategy will depend on whether the person is likely to have developed that shared identity or not. So in terms of the results, I intentionally cherry-picked one where that shows how the adaptive identity is best. But basically, the results are, it really depends when the robot will have the maximum effect. So in situation where we have a lot of first responders, so if you have a lot of emergency services available, the robot won't make a big difference, and which is expected. So if you have, a lot of trained and professional available, the help of others is less critical. In situation as well where basically everybody is injured, the robot doesn't make also a difference because there is not enough people to help. But here, where we see that the evacuation time is reduced with IDEA, is in cases where there isn't enough of the first responders, and the criticality is not as, 60% of people are injured. And actually, this is representative of a lot of incidents where, the emergency services are stretched, and that cooperation can really make a difference. So kind of summing up, what we did is we had social group that have markers. We built an identity estimator that kind of forecast their likelihood to have developed that shared identity that pushes people to cooperate. Based on that, we built a game. The solving of the game lead us to the optimal strategy for the AI agent to coordinate the response. So on the positive side, we were able to enable the reasoning about identity for collaboration and for improved results in very specific context. However, on the other side, we didn't enable safety guarantees. So it is an optimal strategy under those assumptions, but can we prove, for example, specific, threshold specific safety properties? And we weren't able to do it. So that's what we then look for in the second topic. And just kind of, I'm gonna pause a little bit in case there is a burning question. Bertrand, do you want me to take a question or to continue?
I think you can continue because I don't see any hand raised or I don't see any question on the chat. So please continue.
Okay, good. So the second level is then how do we enable those safety guarantees? So kind of summarizing, what we did is we used really a game-theoretic model to be able to find the optimal strategy for achieving certain measures. Now, if we approach it from another way, from goals, we have a set of goals, and then we want some properties. We want some safety properties. So, for example, we want the evacuation time to always be below a certain threshold. Or we want to not assume that, for example, which is often the case with game theory, is it's a game of rational agents. All agents are rational. So we want to kind of say, well, a proportion of those people are rational and some other are not. So we want to kind of change those assumptions, and we want to provide guarantees. So if we model it, then we have an environment where there are actions that we can observe. So we can see what people, we can hear what people are saying. We can see how people are moving. There are things that are inherently uncertain. So we don't know who has developed the shared identity, who is likely to help whom. So this is a kind of inherent uncertainty. And then we have some controllable actions. So the robot can take specific actions for coordinating the different team. So, and that can be formalized as, finding an M, so finding a strategy in a given environment, so environment where there are some observable actions, there are some uncertain actions, and to achieve a set of goals. So the goals that we really specify, whether they are optimization measures or computation, safety properties, or and under certain assumptions. So how do we do it? Then we have to trade off basically performance and safety. So we can still model it as a game. So you have uncontrollable action by the environments. So which contain the environment as in the broadest term. So where people are part of that environment. We have a payoff, we have a cost of doing certain actions and also a utility. So the utility can be, that kind of, for example, the term, the evacuation time, the number of evacuation, and then we have a probability. So there is an uncertainty about the behavior of each entity and in the environment, and that's what we use. So, and then there are also time overhead for taking each decision. And that's what we can formalize as a synthesis problem, but with two levels. So at design time, we built a model of the environment. So the people, maybe the topology as well, but the identity and how people form groups is not known. And then at runtime, we can evaluate by identity and synthesize the appropriate strategy. So in terms of the modeling, what we did, we used probabilistic modeling, and there are multiple categories of actions that are included. So first, there are really the uncontrollable and actually even not partially observable actions. So, whether a developer, whether a survivor, a person there developed a shared identity that belonging to the group or not, we only as a kind of evaluate it based on different markers. And then based on that, we have the controllable action. So the thing that the robot can do to help the coordination. It can ask a person to help. It can contact the first responders. And then based on that, we have a set of still uncontrollable but observable action. So we can see whether when the robot asks someone to help, whether they are helping or not. We can see whether they are actually kind of rational in the sense of their helping behavior or not. And what we do is also to calculate the payoff. So GI is the group identity that is created, and that depends on, it depends on whether the shared identity has emerged or not. So in the case, for example, where the shared identity has emerged, then we can see, for example, that the preferable action is to ask the person to help the victim rather than calling the zero responders. And in cases, so in the simple cases where clearly the shared identity is not there, it's a pro-self person, then, for example, the best strategy is to contact staff to contact first responders. So that kind of give an illustration of how the payoff works. But all in all, what it means is we still have social group. We do the identity estimator, and there is a game and solver. But rather than doing that, we directly from the identity use a modeling and verification tool to synthesize the strategy and deploy it, so that it satisfies the given safety properties. So the question then is, how do the two strategies compare? So can the formally verified strategy be computed, for example, at runtime? So what we did is we compared, for example, IDEA, which is based on, game-theoretic model, and Formidable, which uses actually a modeling and verification tool, and see how the evacuation time compare. And it's in the same case as before, where IDEA performed a little bit better than others. So this is where there is a lot of staff support. So in this case, actually the measures are comparable, but with the added benefit of verified strategy. In this case, we also compare, for example, when you add multiple measures. So here we're optimizing not only in terms of the safety and the evacuation time, but also the numbers of calls to the first responders, because we know that first responders are a scarce resource. So we want to minimize the number of times we actually call the first responders. And we can see that when you add multiple properties, that actually the synthesis is better optimized in terms of the time. Same as much as we increase the number of survivors or number of victims, it scales pretty well. So it still explodes, but it can go in terms of seconds, even with the large numbers of evacuation. So summarizing, what we did is really going from groups, but rather than building a game-theoretic model for creating a strategy for the autonomous system to coordinate multiple people, now by using modeling and verification, we are able to synthesize and verify that strategy for the autonomous system. So in a way, we're not only creating an optimal strategy, but also synthesizing a verified one, so we can guarantee those safety properties, but they can be achieved or not. But however, there is a kind of a dependency, because the identity estimator is probabilistic, and it doesn't, when we do the verification, it doesn't account for the uncertainty of the estimator itself. So the question is, how do we kind of align as well the safety properties with the safety properties of, for example, this language-driven estimator? And that leads me to the third part of the
can we
Yes.
stop for 1 second? I haven't seen the people raising hands, but I have some questions.
Okay.
I have 3 questions, so maybe you can answer quickly. First, I'm not sure to understand clearly what it means to verify a strategy. I see that you're using this verification tool, but I'm not sure what it means to do the verification of a strategy. The second question, if I understand well, you only have one robot in your simulation, not multi-agents. And my third question is about the simulated people groups. What is the behavior model that you have inside? So we've seen behavior model for the robot, but I'm not sure to have seen what is the behavior model for the people.
Okay, so the first question is, what is the verification? So what we're verifying are properties, probabilistic properties. So things like the evacuation time will be below a certain threshold, or properties such as children will be evacuated first.
Okay, you verify the outcome of the strategy.
Yes.
Thank you.
Yes. So there, I mean, and for example, threshold maybe we cannot synthesize that
Okay.
or so we're taking those properties. And so those are this, yeah.
So there's only one robot, one, right?
Yeah. So what happens is we have only one robot at a time. So the strategy now is not coordinating multiple robots.
Okay.
So one of the things is we're thinking about is that non-dyadic interaction. So at the moment, it's one robot thinking about going to a survivor and making a decision. So it's not multiple robots coming together and helping the person.
Okay, that would be interesting. But, so what is the behavior model of the people?
So the behavior model of the people, and that's the one we don't control. So that's the one we use. We use agent-based model from social psychology to just observe. So we observe it, and that's kind of the modeling how people, depending on multiple markers. So the markers they use is cultural clusters. They use gender, age, all the demographics, and they defines ways of likelihood of people helping one another, but based on what is seen in empirical data.
There's a question from Luis Angel Rivera. Is the level of danger contemplated, and how does it affect the behavior of the model and of the identity agents?
The danger.
The level of danger.
Yeah,
do you look at the level of danger, in fact?
No. That element of level of danger is not explicitly modeled as a variable. However, what they have is they have, like in the agent-based model of the social groups, what they have is they have a criticality measure, and the criticality measures will kind of control how many people get injured and how long do they take to move again.
So then it is taken into account, I think. Because what you call criticality can be understood as the level of danger.
Maybe, but danger, it can be dangerous, but still not a lot of people get injured.
I will just check if Luis Angel Rivera is happy with your answer. Do you want to add anything, Luis Angel? I don't see. So please, so let's go on.
Okay, I'll just take a sip of water. And here we go. Okay. So I move to the last bit, and that kind of shifts. So just to go back, what we say is a little bit, as well as Bertrand was asking, is those safety properties are not dependent also on, what kind of system are we using? What is the uncertainty of those systems? So the last bit I wanted to discuss is when we talk about requirement of those systems that learn, is we focus a lot on defining specific objective for the system. So whether it's accuracy, for example, or other things. But failure of those systems is not only of not achieving their objective. So if we take an example in this book that I really like, is in social media, for example, where if you set the objective as maximizing the number of clicks, a lot of recommender systems are actually achieving their objective of maximizing clicks, but they might be doing it by actually the environment. So if the machine sees that by promoting extreme views, then you have more click, then that's the strategy you adopt. So a better formulation would be that we're not only building or engineering, or we don't only want machines that are whose actions satisfy or achieve objectives, but also who's actually achieve our objective. But then become the question is how to specify our objectives for machines that learn but also fail, because failure is part of the game of a lot of those machine learning systems. So, and the question we are going to is how then we specify. So how do we create those requirements that allows us to say whether a machine learning or an AI system is actually satisfy some goals. So a lot of the work, at least in requirements engineering so far, is always bringing the problem and solution space, but also trying to divide and conquer, specify, and then build machines that satisfy the goal. So it's always, even in the previous one, we're always trying to find a machine, S, that in a given environment satisfy the goals. So we're kind of creating this strategy for the robot to satisfy the goals that are already specified, whether it's minimizing evacuation time or prioritizing children or doing other specification. However, a lot of sometimes that specification has also to adapt to different environments. So when we do adaptation, it's still a different environment. You still need to create another strategy, but the goal is stable. But then one of the things is what happens if you cannot build a certain strategy, for example. And a lot of the work, again, in requirement is actually then relaxing that goals and understanding how we relax the goals. So when it comes to ML, one of the things is no longer about just kind of specifying what we want and then building to achieve it, but actually it's around understanding and aligning what we want with the objective and what we can implement to achieve. So, and one solution to what we are exploring is, rather than just specify and then implement and see what you have, is trying to build an iterative process by which we want to find actually not only a specification, but a specification and a goal together that go together and align better. So when a failure is defined, then you can either repair the machine or actually revise and repair the requirements so that they align. And in this case, what we do is not the kind of traditional thing going from requirement to implementation, but also identifying failure, trying to implement it as obstacle, mitigating, identifying failure again, on that set. So we played with it for an autonomous driving example, a very simple one, and it's basically, for example, a lot of perception component will have different measures between adult and children. So understanding how this works, understanding where it can affect the system is really important. And sometimes as well, depending on how you do the parameter, like you calibrate model you make, like for example, to uncomfortable driving experience, so something like braking unnecessary. So you need also to mitigate those multiple goals. So finding not only what we want to do, but actually this correspondence between the objectives and the implementation. So I have a small example here between the adult and the children. So for example, when we tried specifically just, rather than going with a pedestrian, then you have to specify, under which size, which crossing behavior, and you end up refining it until you understand better actually your design your design space, so all the assumptions and where your implementation work or not for the specific environment. So, and actually kind of looping back to the beginning, kind of moving from just collaboration as in goals into actually reflecting on the goals we're creating, the AI is achieving. So moving from, collaboration or synthesis to create into that reflective level where the output is not, you're not only about the goal, but actually updating it, aligning it with what we do. And that's kind of where we are. So kind of summarizing is we started from just the ability to reason about and enable collaboration. Then we discovered that safety is important. So how do we try to achieve safety through, for example, synthesis, but then also understanding how to align with a certain specification and enable humans not only to engage in the effort of the collaboration, but also in the reflective part. And so allyship is the next level. And then thank you. That's kind of a lot of my collaborators at the Open University, Lancaster, and Polytechnic. Thank you very much.
Okay, let's open the discussion. We have 10 minutes. As I wrote in the comments, Patrick will be with us at 5 o'clock European time, so he will give a presentation after you, which is good. Thank you. Amel, I'm not sure for the last part. So I appreciate the fact that you try to implement the ideas of Stuart Russell. He has also some approach to these questions of alignment of objectives of one single AI entity or several entities with human behaviors. But I'm not sure to which level, what level you have reached in terms of possibility of application. The example that you have shown with the self-driving car, I'm not sure whether. So, does it implement these ideas exactly on?
Yes. So far, what we did is we try. So what we're doing is building the autonomous driving car and the implementation. You can control it up to a certain point, but it will always fail in certain cases, right? So what we're trying to do is in which cases it fail, and can we implement guardrails, other measures that can compensate for those failures. So for example, no matter what data you use, if you don't have a LiDAR on your autonomous driving car and someone is crossing in the dark without reflective clothes, the car won't stop. So understanding that, this is a domain where the car will fail, and then put other measures outside. So, for example,
I'm not sure if the European Commission will like this idea of failure and compensation and mitigation, because in the AI Act and in the supporting standards, we will be asked to, let's say, to remove all possibilities of failure beforehand, which is of course impossible, by the way, but that's how they organize things.
I mean, the thing is we shouldn't be complacent. If there is a method to remove it, yes, definitely. But actually understanding the fail operational rather than just fail safe is important. So therefore, in the autonomous driving car, for example, there are cases where the fail safe mechanisms was like, just go on the side and park. And that created a lot of problems. So for example, was it the Waymo that kind of dragged someone because that was the fail-safe measure that was implemented. So for us, we're trying to understand those mechanisms a little bit better and align what the claims about what the technology does and what the implementation really does.
Okay, I don't want to be the only one to ask questions and discuss with you. We still have a few minutes. Patrick is with us already, but we have still a few minutes if you want to take the opportunity to ask a question to Amel. Yeah, okay, I have on the chat, I see 2 questions by Juan David Dugan. How do you manage priority change management on the tasks, like urgency of one new task against ongoing tasks? So that's the first question.
So we don't have a preemptive way. So if we deploy the strategy, the only way that you can deploy another strategy is to compute from scratch. So it's not incremental, is you do only one strategy at a time. So if I understood well, it's like, there is a new strategy while you're a new task or a change in the environment while you're executing the strategy, right?
Yeah, exactly, yeah. It's how you manage the ongoing task when a new one becomes more important.
Yeah. So with this one, we in this specific context in the synthesis, because we were doing really kind of the macro level, how you deploy it and implement it, we didn't necessarily do it. But actually, we have another work that was really looking only at that proactive and reactive adaptation and trying to predict which task is likely to go in the different environments and adapting. So, but in this work, basically, you synthesize your strategy, and once it's being run, it's not interrupted.
You want to ask your second question, Juan David?
Well, yes, it's quite linked. Is how to manage contradictory environmental signals in the sense where the robot is I suppose, is having several sensors, and the environment can have several signals, and for some 2 persons that are going in the 2 opposite directions, how I select, etc. So yeah.
How I select which person to contact for this specific.
Yeah, for example.
Yeah. So actually, we calculate for each person the likelihood to help, and then if 2 people, for example, have the same likelihood to help, then we pick one randomly. So it's not. Yeah.
Maybe the last question by Luis Angel Rivera. Maybe I can read the question. Is level of alignment to user objectives with agents' objectives measured? If not, how would you measure it? And then maybe I don't see the end of. Sorry. Like misunderstanding of our goals, what the agent finds optimal, but we find unacceptable. I'm not sure to have understood the question, but maybe did you?
Well, this is a super difficult question. So one of the things is so what we do is we try to make everything explicit first, and that already kind of highlight the assumptions that are made by the machine. And once you make explicit those assumptions, then the first step is that us or the stakeholders can assess whether it's acceptable or not. So this is the level where we are making as many explicit assumptions and domain properties, extracting those, and then leaving it to the person to say whether, okay, this is acceptable or this is unacceptable. So the goal, the way we measure that alignment at the moment, at least, is by extracting as many information as possible that wasn't explicit, and then making it explicit and seeing whether the stakeholders find it acceptable or not.
Yeah, it's a difficult subject. It's going to take some time to solve it, if we are able to solve it. Okay, thank you.